Our next lesson is on the kinetic molecular theory. I have divided this into two parts, but this is the kinetic molecular theory of gases. And in this part, we're just going to introduce to you the concept of what the kinetic molecular theory is. Let me grab my remote here. Okay, so there are what the kinetic molecular theory does is it explains what's happening on the molecular level. No, let's say it this way. It's looking at what's happening on the molecular level to explain what we observe on our level. So we observe things like when you increase the volume, the pressure drops. We learned and observed things like when the temperature goes down, the volume goes down. These were laws. They happen this way, they're observed this way, and they're always this way. But when we get to the theory, we're trying to say, okay, what's happening down on the molecular level? What's happening with those molecules that as the temperature drops, the volume is naturally going to get smaller? Or what is happening down on the molecular level that when you bring up the volume, the pressure is going to drop down? And this is helping us understand on the molecular level and the motion of the molecules, that's the kinetic part, what's happening to explain the behavior that we observe. Okay? So it has various statements. We're going to walk through and talk through the statements of the kinetic molecular theory. The first one says that a gas is made up of molecules that are separated by very, very, very large distances between them. These distances between them is much, much greater than the size of the molecules themselves. So we say, you know what, those molecules are just not contributing any of taking up any space inside that container, which at first seems kind of bizarre. But let's consider what we mean here. If a molecule is about the size of a marble, so just consider that for just a minute, the next nearest molecule would not be in the room you're in, okay? It would probably be a couple rooms over, and maybe one flight of stairs up would be the next nearest molecule. We're talking vast, vast distances between them. So let's just consider your room. If we considered the volume of your room, your chair's taking up space, and we could subtract that out. Your desk is taking up space, we could subtract that out. But in terms of the measurement of volume, does that little marble really make any difference? Well, it doesn't. That's what we mean by negligible, okay? So when we consider the volume of a container, we consider that volume as just empty space. The atoms, molecules themselves don't contribute enough space in there to even consider. Okay, that's one statement of the kinetic molecular theory. The next one, when you consider those molecules in motion and you consider the temperature of those molecules, okay, that the kinetic energy of those molecules is going to be directly proportional to the temperature of that container as long as you're in the units of Kelvin, okay? So if we have a low temperature, the kinetic energy of the molecules are low. If we have a high temperature, the kinetic energy of the molecules are high. Okay, and there's going to be a formula that we need to write there, so I'm going to write it here that you can write it into your notes at this point, and that is that kinetic energy equals 1/2 mass times the velocity squared. The average speed, oh, that doesn't give it to me. Let's say this. We'll worry about that equation later. Kinetic energy is proportional to temperature. That's all that was going to go in there. I'm sorry, we'll come back to that equation a little bit later. Okay? Third statement is that the molecules are in constant random motion and that their collisions are perfectly elastic. So those molecules are flying through space, okay? So they're flying through space and they may be on a collision course with another molecule and they collide. What does it mean that they're perfectly elastic? When they collide with each other, they're going to bounce off. And they're not going to lose any energy in the process. They can exchange energy. So maybe this one was traveling really fast and this one was kind of going slowly. When they bounce off, there might be some average speed that they're going to travel as they ricochet off of each other, but they're not going to lose any speed overall. They're not going to lose any energy overall. What is that good for? Well, we've got the gas surrounding us and they're bouncing off of each other and they're on their merry way and they're bouncing off the walls of the container, which is our building walls, but they're not slowing down. If they did, that would be bad because then they'd be all down there on the bottom of the floor as a liquid and that wouldn't work very well for us. But this is not the way we're used to collisions happening. If you think about playing pool, all right, you play pool, you hit the balls and they bounce off of each other, and if one's going fast and one is sitting there, then they're both going to bounce off, kind of one slows down and one speeds up, but eventually they're going to stop moving. They're going to be losing energy. Well, that does not happen. There's no loss to friction. They just collide and they exchange energy, and that's what we mean by perfectly elastic. Now there is, oh, I was going to write that formula down there. So let's go back and revisit what we have here. We say the kinetic energy is proportional to temperature, but we also know that kinetic energy is a relationship of the mass of those things that are moving and the velocity of those things that are moving. Now there is a whole bunch of these molecules inside of this container. Many, many, many of them. So what we say is, on average, if we take the average speed of those, then it's going to be equal to the average kinetic energy, and that average kinetic energy of all the molecules is going to be proportional to the temperature inside of there. So as they speed up, they have higher kinetic energy. As they have higher kinetic energy, they have a higher temperature. Another way of saying it, we take a container, we raise the temperature. If we raise the temperature, the kinetic energy is going up. If the kinetic energy is going up, the only way that's happening is because they're now moving faster. We're not changing their mass. They're the same old molecules they always were. But if you're raising the temperature, you're raising the kinetic energy. If you're raising the kinetic energy, you are speeding those molecules up. So that's what's happening on the molecular level that accounts for the behavior that we see. Okay, so let's look at those statements and let's consider a gas here. One's at a low pressure and the other one is at a high pressure, okay? And let us think about the statements that we already knew about from the beginning of this chapter. And that is, where does pressure come from? Pressure is a result of, and we had talked about this not in terms of kinetic molecular theory, but what is pressure a result of in terms of the molecules? It is collisions between the molecules and the walls of the container. So if you have more collisions, you're going to have higher pressure. If those collisions are being hit with more force, then you're going to have a higher pressure as well. So pressure is dependent upon two things. It's dependent upon the frequency of the collisions per unit area, and how hard they are striking that. And you have got to keep that in mind as we think about what's happening on the molecular level. That the way you have pressure is you have collisions, number of collisions, as it goes up the pressure is going to go up, or the force with which they strike it. As the force hits higher, then you're going to have a higher pressure. Keeping those things in mind, okay, which one of those statements, 1, 2, or 3, and it says enter a number. I want you to do this instead. I want you to, and I'll write on the screen here, I want you to answer A, well, what's going on? Try again. I want you to enter A if it is statement number 1 that explains why they're compressible. I want you to enter B if you think statement number 2 explains why they're compressible. And I want you to enter number C if you think it's statement number 3 that defines why they would be compressible. Stop, think about it, look back at those statements, and then choose one. Okay, did you choose A? If you chose A, you're correct. What was statement A? Well, let's flip back and look at statement A real quick. I'll back it up, find it here. Boop, there it is. Molecules are separated by very, very, very big distances between them. So if one is here and one is 2 rooms over here, it's easy to push them together and make them take up less space. That will define why they are easily compressible. So we know that gases are easily compressible. That is a property of gases. Now we can explain why that would be true if we understand what those molecules are doing down on the molecular level. Okay, let's go back to where we were. Okay, now we're going to talk through a few more here. We just did compressibility of a gas. Let's think about Boyle's law. What is happening with Boyle's law that helps us understand why gases would be compressible? Well, let's get rid of that little dot there and let's think about what Boyle's law states. So let's take a picture. All right, so I have a cylinder with some gas in there, okay? And those molecules are moving around and bouncing off the walls of the container and hitting it and bouncing around, and they're striking with a certain amount of force, okay? And it's giving us a certain pressure that we can measure with a pressure gauge on that. Now, Boyle's law says that if we were to take that container, and it doesn't matter whether we could either increase the volume or decrease the volume. Let's increase the volume, okay? So if we increase the volume, we still have the same number of molecules buzzing around in that container, okay? They are still moving at the same speed, and they're striking the container walls. They're not moving any faster, so they're not striking with more force. How about the frequency of the collisions? The container is bigger. They have to travel a greater distance before they're going to strike an edge. So what would that do to the frequency of the collisions per unit area? Well, the frequency would drop. If the frequency would drop, then the pressure is going to drop. So as the volume went up, kinetic molecular theory would tell me that the pressure would certainly have to go down, because the number of collisions, let's just consider this little area up here of the top of this container, the number of collisions is going to go down, and that is going to drop the pressure. So you should be able to go through any of these statements. Charles's law, that's the relationship between volume and temperature. As the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. You want to think about what's happening on the molecular level that explains that. You could consider it in terms of Avogadro's law. You take a balloon and you're blowing it up, okay, and you got your lips on here and you're blowing, and you put more and more in there. We know the balloon gets bigger and bigger. Let's think about why. It's a constant pressure pushing out here, so the force of the collisions has to stay the same. The number of collisions per unit area has to stay the same. Why would the volume have to go up as you put more moles of gas in there? It would also help us explain Dalton's law of partial pressure. And we looked at, when we defined Dalton's law of partial pressure, we really looked at the molecular theory with our image for that one. So you could go back and look at the picture and say, okay, it helps explain why the sum of those pressures would give you the total pressure. Now, I want to leave you with a little activity that you need to do, and then we're going to think about an overarching theme that we have going on in chemistry from here forward. Okay? There is on page 224 to 226 a derivation of PV equals nRT, starting with kinetic molecular theory and building it. Where did we get PV equals nRT? We took all of our laws. We took Boyle's law. We took Charles's law. We took Avogadro's law, mathematically combined them together, and that gave us PV equals nRT. The derivation in the book takes the statement of the kinetic molecular theory and gets you to PV equals nRT. Now I want you to just look over it. I want you to try to grasp how they got to PV equals nRT using the kinetic molecular theory. I don't want you to memorize any of that stuff. I just want you to read through it and see that it is possible to get there using the concepts of what's happening on the molecular level. Having said that, I want us to turn to this image. This is an image that I created that really is explaining for us connections that we see all the time in chemistry. So what we have is we make observations. And when we make observations, that tells us things that we see on the macroscopic level. With our gas laws, we learned that pressure times volume is a constant, okay? Or Boyle's law. We observe that. We can make measurements. So the macroscopic property is what we see. So there's glasses. It's making measurements and observing. And a lot of times this macroscopic gives us the laws that we have. We make observations and we come up with laws for it. Now, if you've got a scientific mind, you make observations and you're not satisfied with that, you want to know what's happening that causes that. So you're getting down here on what's happening on the particulate level, okay? That would be the molecular level, the atomic level, what's happening with the things down there on that level. So I've got an image of molecules moving about. The lines that you see here are actually energy levels of electrons, but we can kind of make an explanation, and very often we have this is the theoretical level, what explains for us what we observe on the macroscopic level. So there needs to be connections between that. Students very often will memorize what they were needed to know about what's happening on the macroscopic level. They're memorizing the laws, okay? Students will very often then go and memorize theories. Okay, so there's the statements of the kinetic molecular theory, and they memorize those. But they don't take the time to observe the connections and think about those connections. This is an important part of really understanding general chemistry, is seeing that connection. Okay? Now, let's consider over on the right-hand side. When we had laws, we came up with mathematical laws, okay? We came up with mathematical equations, and I started out by writing this one that they're proportional, but really the mathematical equation that we came up with looked like this, right? So we came up with ways of expressing what we observed on the mathematical level. I want you never to just memorize an equation without understanding the connection. So do you understand when you see that this is saying that as the pressure goes up, the volume has to go down? This is explaining mathematically, right here, it's explaining mathematically what we observed with our eyes and observed with measurements that we made. So don't just memorize. Again, students like to memorize. They memorize that, but you ought to be able to understand that this is giving us a connection between what we observed. And if it is rounded out properly, we could also explain, and this is what we just finished with, what's happening on the particular level and help us to get the connections that we see mathematically. So why does the pressure, when the pressure goes up, the volume goes down? Well, we could explain it using the theory. So all of these connections is what I want you to be able to make. I don't want you to memorize, 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 and not make connections. This making connections is time spent thinking, okay? Now, I shouldn't have to say we have to think in chemistry. I bet most of you know that. But we don't take the time to think about it. Thinking about it. You might want to explain it out loud verbally. Verbalize it. These connections. Talk about them. Even if it's just to your dog at home. Say, let me tell you about how P1V1 equals P2V2 mathematically explains what I see macroscopically and explains what I see on the particulate level. Now this is something that I've drawn out for this chapter, but I will revisit this concept of being able to understand connections between macroscopic level observations, particulate level explanations, and mathematical equations. I want you to be able to spend time thinking about those connections and not just memorize facts and not make those connections. At any point, when you don't understand those connections and you can't really verbalize what's happening between them, I've got one last very important thing to write down there, okay? If you can't do this, come see me. Don't come up with shortcuts. Don't come up with little mnemonic devices on the memorized level. If you can't see those connections, if you cannot do the part where I have exclamation points, I want to have a discussion with you. We'll talk about it in class or in my office and think about these connections. So there's never one assignment that says, I want you to explain these connections, but that is what makes general chemistry general chemistry. Okay, so this kind of wraps up kinetic molecular theory Part 1.